Thanks, Sanjeev. Yeah, so I'll be talking today about using language models for instruction-based IR. And let's see if this works. It doesn't. Okay, cool. So yeah, if you think of information retrieval, you're probably thinking something like Google, right? This is actually Google in 1999. So actually it doesn't look too different from what you might see today if you type into Google. Then if you look at, so the Google that we all know and love, you type in your keywords, you get back your search, and so on. If you're a little more up to date on information retrieval, perhaps you've heard of things like Search GPT, where you type in, again, your query, but then this is going to go throw it all into GPT-4 and then give you some results. And along the same lines, you might have something like Perplexity, where if you type in who invented the toaster, you're going to get this nice little answer with citations and all these different sources here instead of in the nice Google-like list. And so we have all these things for information retrieval these days. There's been a lot of hype about how language models are going to take over information retrieval. Google's going to die. But despite all this, search really hasn't changed, right? So all these new things are actually mainly just adding a wrapper around the results, right? You have Search GPT, you give all the search results to an LM. You have Perplexity, you give all the results to an LM. But the core search itself is still very similar to what we see in 1999. And so what is the state of search these days? Well, keyword search is still a really strong baseline. That's something like TF-IDF or BM25, where you just do a bag of words and try to figure out how similar things are that way. And then probably neural age 2017 plus, you can match semantic keywords. So if you type in Apple, it might know you're talking about the search company. It might know you're or the technology company. It might know you're also talking about the fruit, depending on the context. And so these days, if you want to build a really fancy RAG system like every startup in AI is doing, or at least a lot of them, you have your really complex question you put in the top. And then what it's going to do is it's going to think about it and break it down into a bunch of different queries. And then it's going to shove all those into your final language model. And so this is all great. We can continue to work on building the language model, make it so there's no hallucinations, so it can take advantage of all these documents we're throwing into it. But at some point, if you have billions of documents, the bottleneck is not the language model. The bottleneck is going to be the actual search. And so what if you miss the really important document out of that billion and it doesn't hit the language model? Well, then you're not going to get your answer. And so what are these type of queries that maybe aren't being found by traditional search? One of them is, I think, meta-level queries. So this is something where you have some characteristics of the document you want to find, but that maybe you can't find through keywords. So an example could be something like, I want a 2-sentence quip that describes a negative sentiment joke about a politician. If you type this into Google, unless there's a website that specifically is talking about 2-sentence quips, it's not going to match on the sentences or the length or the sentiment or anything like that. Another example might be some complex and/or queries, where you have something like, what city is its own county and it's based on the East Coast and is not located in New Jersey. And so again, if you put this into Google search, it's going to try to keyword match this in semantic space. And maybe it'll find you the answer, but it's not actually using these logical conditions in any reasoning-based fashion. And so why can't search have all the capabilities a language model can, right? And this is especially useful if, say, perhaps you want to take that really complex question and you could just give it to one model that's like an LM, and it could just do that one search, saving you a lot of time and effort. Or maybe if it really is a hard question, it could do a lot of searches, but it actually has the power to be able to reason over each document and find the correct ones. So we want these retrievers that can take instructions just like language models. And the good news for us is that retrieval models already use these language models. They're already building retrievers based off Mistral, based off Llama. And so that's kind of the hot thing that's in vogue right now. And we're already using it. So why can't we just use them just like we would a language model? And so that's the goal that I'm going to talk about today. And I'll talk about it in two ways. First, evaluation. Maybe we really could use them like this today. And so I'll talk about some discussion of how we evaluate them. And then as well, some work about building a model that can do this. So let's talk about evaluation. This is a paper, Follower, Evaluating and Teaching Information Retrieval Models to Follow Instructions, from my advisors here at Hopkins, as well as those at the Allen Institute for AI and the University of Glasgow. And so we're looking to evaluate these models, we want to find some, ideally, some human written instructions for search. And that might be kind of hard because if you're like me, you're not typing in really long instructions on Google search, so you can't really go mine them. They're not really on like Reddit or something. You can't really find them that way. But there is one source. And if you've heard of the TREC community, it's the Text Retrieval Conference in Information Retrieval. And what they do is they have a big shared task or a bunch of shared tasks every year. And the government, the National Institute of Science and Technology, actually funds them to be able to build these annotations. And so what's really cool is that they take all these queries that the shared task organizers create, and then they pay for humans to go through and annotate all these documents and say, is this relevant to my query or not? And the really neat thing is, so along with this query, which you would see in any just standard search-based system, they also include what they call a narrative. And this is actually just a long-form instruction that they actually give the humans. And so as an example, here's this one about the British Channel. And 90% of the instructions have these complex and or conditions here. They want things about the projected impact on the lifestyle or major changes to transportation systems. It also includes elements like background info. So maybe the human annotators have never heard of the British Channel, so you want to give us a background, but you don't really need this to answer the question if you're familiar. And then finally, they have some documents you don't want to include, like expense reports or schedule changes, etc. And so we give this, or TREC gives this to the humans to annotate, but then they never give it to the models. The models only ever see the query. So what we decided to do is to give this all to the retrieval model. So we're going to give the query and this instruction, this really long form thing, to a retrieval model and see how it does. And similar to how you would prompt GPT, this is all specific to the query. It's not some generic instruction. It's very specific to the specific one. Cool. So just some quick background details. You can see that here, the length of the query is about 10 to 15 words. The instruction gets quite longer. It's between 40 to 70. And there's about 50 to 180 relevant documents per query. So there's a lot of relevant documents. We change about half of those in our evaluation, which requires a lot of reading, a lot of documents to read. Because we take each of these relevant documents and we're going to change the instruction and then re-annotate only the relevant ones. So in some cases, we read like 100 documents per query and then had to decide if they're relevant or not. It's pretty tedious, I will not lie.
Sorry, I'm not sure I'm quite following.
Yeah, let me explain. I think I brought that up a little too soon. So here's our annotation and evaluation process. So you take the query, and then you take the instruction they give. And so what we're going to do is we're going to change the instruction just a little bit here in red. We're going to add the words, if they relied solely on the Hubble. And then we have both the original instruction and this changed instruction. And so then we can then go through all the documents that were relevant before. So here's document 1 through N. And document 1 here has ideas from both the Hubble and the Cosmic Explorer. So you can see it doesn't rely solely on the Hubble. So then we're going to take the original instruction and the changed instruction and see if the model changes its definition of relevance based on that. So it should be relevant in the first case, and it shouldn't be relevant in the second case. Does that answer your question?
I think so. So the original instruction comes from the TREC people, and the changed instruction is something that you guys just made up out of your heads.
Yes.
The original instruction, the TREC people made up out of their heads probably, but none of this was generated by language models or anything.
Correct, yeah.
What's the motivation for that change? Like,
Yeah.
you change it, it's just some arbitrary change? Or?
Yeah, so the goal was to make about half of the relevant documents no longer relevant so that we can measure the sensitivity.
Just try to find a subtle difference, I think.
Yeah.
And it makes like 50%, which is pretty substantial.
Yeah, so about half the documents would be not relevant. And so then the goal is to not only can you find the correct documents, but does it change correctly with that instruction? Is there that sensitivity to instructions that we expect with language models?
So the way that you've made the changes is you're saying the original relevant documents have become irrelevant. So that's do you also have try to get changes that do the other way around, where so basically you've introduced precision errors in the old if you were to use the results from the old query.
Yeah,
how about recall errors?
That's a really great question. So the corpus has like 3 million documents. If we were to look for the other way, then we would have to look through 3 million documents, which is kind of expensive. So we only added changes that makes it more specific. So we only had to look at the relevant documents and cut those in half. Yeah, great question. Yeah.
When the TREC annotated this, there were two things. One is
the person who framed the query was the same person who answered it.
Absolutely.
It makes a huge difference. There's a lot of like literature on it.
Yeah.
We change the query like this. Some interactors say this is not an ecologically valid query anymore. And it's a legitimate thing because the literature is showing that when researchers do this, they don't accurately reflect what people want. Let's put that aside. For annotations, they do this pool judgment, where they use a bunch of search engines, retrieve documents, do some union of the top 10, 100,000, something.
Yeah.
And then the annotate. If you look at that list is not very long. It's of the order of a few hundred documents per query. And
Per
you could
system.
do what Jason is saying,
Yeah.
just on that. And Trek does assume that anything that's not on the list, by definition, is not relevant. And they know that that hurts their recall measure a little bit. It overestimates the recall, but that's something that they measure.
Yeah.
To be accepted.
Absolutely. Yeah, we had the same person who annotate all the documents. So we keep some of that relevance, but you're right that we can't go back and find the person in 2010 who wrote this instruction. Yeah. Yeah, thank you. So let me talk about how models do on this. First, a little bit of background on retrieval, if you're not familiar. There's usually two ways of doing this. There's some exceptions, but they usually fall into these groups. The first is the bioencoder on the left. And here, this is what's referred to as like vector search or dense retrieval. You're going to take your documents and queries, you're going to turn them into a vector, that's U and V there, and then do some sort of cosine similarity or mapping to be able to find the relevant documents. On the right, you have a cross encoder. And this is basically just a language model, and you're going to have it output some probability between 0 and 1. And it's usually much better because you can do full attention between query and document, but it's way more expensive because you can't cache the representations and you're using full attention. So on the right, you could actually use GPT-4 as a cross encoder. You couldn't use GPT-4 as a bioencoder unless you changed it a bit and had the weights and such. Yeah, so let me show you how well retrieval models do with following instructions. So here's a bunch of existing retrieval models on the left, and on the bottom is this instruction sensitivity metric that measures whether the model followed the instructions or didn't. And so because you can move the document up or down the ranking, your score can actually go from -100, where you make the document much more relevant, even though now it's not relevant, or to 100, where it's like completely not relevant, which is ideal, or 0 if it just doesn't change based on the instruction. And so a lot of these retrieval models actually make it more relevant when they should be making it less relevant. So they have negative scores. And notice this includes things like Instructor XL, which is supposed to be able to handle instructions, OpenAI's embedding model, BM25, and so on. On the top, there are some retrieval models that actually do correctly follow the instructions. But if you notice, these are actually all large cross-encoder models that are basically just language models, except for this Google Gecko bioencoder, which has a small positive performance. And so overall, they're just really not following these instructions, especially the bioencoders here in the bottom left. And these are very expensive bioencoders. A lot of compute and effort went into them. So why is this? So why are current models bad at this? We looked at two main reasons. So the first is, my intuition was that they're just keyword matching. We give them these instructions and they're actually just ignoring them as instructions, and they're performing this sort of semantic keyword matching. And the second is, well, you might think retrieval models don't usually see long queries, so maybe it's just the length of the query that makes the difference here. So let me talk about these. So current models, this is kind of an aside, but current models use instructions, they say. And part of what prompted me down this path is I thought there's no way these models are actually using them as instructions. So what they do is they take this task here, so like given a claim, find documents that refute the claim, and then they put that before every single query in the whole data set. And then they not only do they use that at test time, they actually also use that at training time. And so they sort of learn these data set representations for each query. So here's like a bunch of them, MS Marco, etc. You notice they all have the same sort of templated format. Given an X, find passages that X. And so they do this at training and test time. And my intuition was really, this is not an instruction they're following. This is just sort of a keyword. And so what we did as an experiment is we took the model and the original query, and we used that with the instruction that they gave, and then changed it to only use one keyword from that instruction. So if it's like find a financial document, I'm going to put the word finance as the keyword. And if you do this, you can see that the models actually do similar or even better when they're using this just one word keyword instead of using an instruction. Except for this E5 Mistral at the bottom, which actually has a pretty strong negative effect to that. But overall, they're like plus or minus 1 point, and they're really just using this instruction as like a keyword for the data set instead of actually using it as an instruction.
And sorry, how do you get to do this comparison? How do you convert the instruction to a keyword?
Manually. Yeah. So yeah, if the thing was about finance, I use the word finance. If it was about science, I use the word science. Yeah. But what about query length? Right, so we could do the same analysis with query length. So I'm going to show here the 3 different types of instruction settings. These were actually generated by GPT. So I took the original truck instructions in dark blue. I then had GPT turn that into a short instruction in the style of the ones they're used to, and then also keywords in light blue. And so if the models get this extra information from the keywords or from the whole instruction, you would see performance get bigger as the color gets darker. But if they don't, then you should see performance go down as the instructions get longer. And so these models on top aren't going to use instructions in training. And you can see that they generally follow this negative pattern. As the instruction gets longer, they have a much worse performance. You can check this for models that do have instructions during training and claim to be instruction retrievers. And it's pretty much the same except for this grid LM model, which performs like pretty well on all of them, no huge difference. And then finally, models that come from an API like OpenAI's or Cohere's, as well as actually just regular LMs here in the bottom right, like Mistral 7B Instruct, etc. And so that's just a crosscoder. I literally took Mistral and I had it do this. And as you would expect, because it's an instruction following model, the more information you give it as instructions, the better it does. And I'll pause here actually if there are any questions. Yeah, Nate.
Are these scores comparable across the models, or is it like the difference compared to using the query with that specific model?
Yeah, they're relative to their own performance. Yeah, great question.
So you have models.
Yeah, I actually don't think I put it into these slides, but the best models are, well, I guess there's some nuance here. Is it best at following instructions or at best at keyword matching? And so it turns out that models like OpenAI's are really good at keyword matching, but they're terrible at instructions. So you kind of have these 2 directions of how you can evaluate them. Cool. Yeah, thanks. So what we did in this paper, it just as a follow-up, is say, well, could we actually train a model that could do this? And so we built a cross encoder, which again is just basically an LM that does probabilities. And we took Mistral here in the bottom right, and we fine-tuned it on some synthetic instruction data and showed that it does really well. In fact, it doubles its performance on this instructor benchmark. And that was just kind of the end of that paper, showing that it is possible to do it. But again, this isn't a bi-encoder model, so you can't use this on like a billion documents. This is just a re-ranker. And so that was mainly what I'm going to show for the next one is a bi-encoder. But yeah, as a summary, current retrieval models just don't use instructions as instructions. They use them as keywords. And so we built this benchmark based off of Trek to measure their ability to follow instructions. And then we trained this cross-encoder, which showed some large gains in instruction following. And bi-encoder models still do poorly. And that really irked me because, you know, you want to use a retriever as a really large thing. So we want it to be able to work across millions and billions of documents. And so that's my next project. Jason, do you have a question? Sorry, I thought I saw a hand. Okay, sorry. Yeah.
The bi-encoder never made any sense to me because you have such a big mismatch between query and document. You already mentioned length.
Yeah.
But it's not, they're not similar. The query and document are not similar. So why would you do cosine distance in their representations?
Yeah, that's a good question. It's kind of back to the old, what's the old NLP saying? If you can't cram the vector into you can't cram the whole meaning into it.
We got a similarity check. So I mean, I know all these sentence embeddings in like cross-lingual space where you have sentence and a translation, and they should get a similar representation because they mean the same. So that makes perfect sense to me. But here, query and a document, they don't mean the same.
But you don't use the same encoder for both. Right? So when you, if I understand right, when you encode the query, you want to get an encoding which will be close to the kinds of documents that would satisfy the query. That's not representing the meaning of the query. It's basically an encoding into documents. Right?
I think that's probably a better intuition for how to look at it. Usually there's like a prefix that says query.
The document might be relevant for all kinds of queries, so that's try to get it the same representation as one query.
Oh, it's not that the document is being coded. I mean, you can't really tell which way around it is, but
Yeah.
the way I
Because
was phrasing it
optimized.
was that
It's
you
not
want,
optimized in the full language. It's optimized.
is that you want the query to be close to the relevant documents. So, imagine you fix the document embeddings first. You can still try to train the queries so that it comes out, the query embedding, so it comes out close to the relevant document. But Orion, you should answer this because
Yeah.
you're the one who actually does it.
No, yeah, great. That's a great answer. You map the query into document space is probably how I
So
would
you first
intuit it.
define something about the specific representation.
You can actually do it at the same time. You use a contrastive loss between
Yeah.
positives and negatives, right? And then it learns to map the queries into document space.
Okay.
Yeah, great question though. It's not as simple as translation where it should be exactly
Yeah,
the
but
same
it's
meaning.
same.
Insert negation into like the background topic, and you put like not finance documents into it. Like the keyword stuff. Like my expectation would be that the keyword would see the performance be stable because it would still have finance as a keyword or something like that. But if it's actually using it as an instruction, then you would see it.
You would see a decrease.
Yeah, like
Yeah.
because I'm just a little concerned about the dichotomy between keyword and sentence here. Like you're talking about something like give me documents that are finance related and just the word finance, I can see interpreting those being basically equivalent, just one is more pithy way of putting the other one. So I'm wondering if there's a way that you try inserting manipulating the background query.
Yeah, that's a great idea. We didn't run that analysis. I have a different paper on negation and retrieval where we show they basically just ignore it. They just ignore the negation entirely. But yeah, that's a great suggestion. Thank you. Perhaps you might have a little more answer in the next one. We did focus on a little more negation in this. Yeah, unless there was other questions on that. Yeah, so turning over. Yeah.
I guess your basic evaluation paradigm is that there was an original ranking of these documents under the original claim. Then you modified it. And what you want is you want a subset of those documents to be ranked higher than the other subset.
Yes.
And you're running all this just on that set of relevant documents, is that right?
Running it on the ranked list that came back.
On the ranked list. So one thing to do possibly would be to take a set of completely irrelevant documents. See the ranking under the original model and apply this and see if the ranking changes. And that's its impact on the general pool of documents, not necessarily relevant documents.
Shouldn't the rank not change because they're not relevant?
Well, something will change. And the thing is that the change that happens there is your baseline for random.
Sure.
And if that has similar trends, that things change roughly the same order of magnitude, then I'm not sure whether you're seeing a real effect or just not.
Yeah, I mean, in the ranked list, some of those documents are
randomly. I'm expecting that list will just be some other random list.
Yeah. Some of the documents in the ranked list already are not relevant, though.
No, that's right. What I'm saying
yeah.
is, since you're focusing on things that are dense in relevant documents, if you want to get a sense of what this does to the background, you should run a contrastive. In this standard hypothesis testing, you just set up a background case and ask. The null hypothesis is it does something random.
Yes.
And so when you run it on a very information-rich subset of documents, you're not sure what you're getting because it could well be chance. I mean, it's a little bit like, if you ran it on an even tighter set, you'd see an even.
Yeah, good point.
So just get a background.
Yeah.
What happens to a random collection of documents?
Yeah, great idea. Thank you. Yeah, so let's talk about modeling. So we talked about these bioencoders, cross encoders. So this work is focused on making this bioencoder that can understand instructions. And so I actually talked to a lot of people about this over the summer in various retrieval different settings. I went to SIG-IR as well. And it seems every time I would talk about, I want to actually give an instruction to the retriever, I got some pretty weird looks. It's just not standard in information retrieval to shove a really long query full of instructions into a retriever. And so let me talk to you about our process for doing that. So in standard retrieval, right, you have this keyword-based search. The current instructable retrievers prepend this prefix in the front, right? But what we wanted was something like this, where you have both a query-specific relevance definition in red And then just to show everyone that you could do it, I wanted to add this purple thing right here, treat it exactly like a language model. I want to make it, give it all the prompt hacks that work on language models and make it work for retrieval as well. So like, be careful in your response and be sure to be correct, and I will tip you $1,000. Or like, you'll lose your job if you don't rank this right, and so on and so forth. So that's the goal here, is to create a promptable retriever that can handle both these query-specific relevance definitions and the prompt. And so this is Promptriever. Instruction-trained retrievers can be prompted like language models. This is joint with my advisors at Hopkins, as well as an internship at Samaya AI. And so what we did was we gathered training data specifically for this. So along with the query and the original positive document, so these are MS Marco. It's a really big standard retrieval training corpus. We then had an LM generate a synthetic instruction that adds some more specificity to this query. So here it also talks about a type of volcanic eruption that has never been seen, but also asks for information about its formation or its characteristics. And so now we have both this query, the positive instruction. We could just train the model on this, and in fact we did. And as you might expect, since the model doesn't actually need this instruction to solve the task, it can kind of just learn to ignore it. And so that's why we're going to add a few more things. But let me first show you some examples of what these instructions look like. And if I just look at the length here of the one with background, that's a really long query. Like, probably a human may or may not actually type this whole thing into a Google search. Maybe they would. Maybe they have some like really specific qualifications. But even if it just works for these shorter ones, having the longer one helps it learn to handle length and could be used for maybe some more synthetic cases where an LM is like augmenting it and so on. So we specifically generated these 3 features along with ones that don't have any of these. So including negation, such as like documents that only mention the name of the town are not relevant. Persona, I'm a history teacher teaching a lesson on the Pledge of Allegiance, or background information like about what substances can be based on. Any questions about what these look like?
The first example,
Yeah.
The second sentence could also have been boldface. That also.
Yes. Yeah, good point. Thanks for pointing that out. Cool. So then the next step is this other crucial component here, is we actually feed all of these into the LM yet again, and we have it generate something that's both instruction positive and query positive. So this is just another good positive document. And then crucially, an instruction negative. And this was actually really tricky to get an LM to do. I tried Llama 3.1 405B, just couldn't do it. GPT-4 Mini couldn't do it. Even GPT-4o, the newest one, could only get it like 2/3 of the time. And this is to generate something that matches the query, but doesn't match the instruction. So you want it to generate something about a volcanic eruption that has not been seen, but that doesn't provide information about the formation. And so we generated a whole bunch of these, filtered them out, so on and so forth to make this training data set, and then trained the model on these with the instructions and the instruction negatives. And so what were our results? First, let me talk about the experimental settings. I wanted to show the retrieval community that this actually works well. And so to do that, I took directly a state-of-the-art retriever called RepLlama. It's based on Llama 2. And I used their same hyperparameters, their same data set. Like, I wanted to show this is as close to apples as you can get. What does instruction training get you? This is MS Marco, like I said. And then we're going to evaluate in domain, out of domain, and also on instructions. And so how does it do on instructions? Here are the same 2 data sets I talked about in the last one, follower and instructor. And cross encoders at the top, the follower 7B was the cross encoder we trained in the last paper. And you can see that there's some pretty large gains on instruction following, as well as standard IR metrics like NDCG. And this is, note, the same model, it's the same data set, it's minus the instructions, and it's the same hyperparameters. And you can get this +14 gain on PMRR, you get +13 on robustness for instructor, as well as 7 points of NDCG, et cetera, et cetera. So it really learns to handle instructions. It's actually even comparable to follower 7B, although we didn't use much data for training it, even though follower 7B is just a cross encoder. So what does it look like, though, if you don't give it instructions? Like, maybe it's just an instruction-centric model. So if you evaluate on MS Marco, there's no instructions here in this retrieval data set. Performance is pretty comparable. It beats it on 1, loses on 2, but fairly similar, despite the fact that there are no instructions and it can handle the instruction case. And so finally, for what I think is one of the funnest experiments, we wanted to test out of domain like you would a language model. So first I'm going to show the retrieval community that we can do it with no instructions. And then secondly, I want to show that we can use a prompt just like you would a language model. And so just like you would a language model, we're going to pick a prompt using a small held out dev set. So we're going to use 10 examples from a dev or train set to optimize over different prompts. And then we're going to pick the best one to show. But some of these beer data sets, they don't actually have dev or training sets. So I'm just going to leave those blank. So I'll show both the best Oracle prompt of the 10 we created, as well as the best one on the dev set if there is a dev set. And as an example, so here are some of the prompts we tried. Like the one I showed at the beginning, be careful when assigning relevance as your job is on the line and I'll give you a $1,000 tip, or think carefully about these conditions when you determine relevance. These are pretty generic, but I would argue they're somewhat generic, like think step by step, or random prompt hacks we all use with LMs. Cool, so this is a very complicated table. Sorry I didn't have time to put this into a nice plot. But at the top we have BM25, RepLlama, and Promptriever. And then I'm going to show with no prompt. Selected prompt means the one that was the best on the dev set. And then best prompt is the Oracle best of the 10. And so the data sets at the top left do have dev sets, and the data sets in the bottom left don't have dev sets. And so it turns out that if you actually optimize over the best 10, that you can pretty much always predict the best prompt just with those 10 dev set examples. For the one of the 7 data sets we can't, we still get a 1-point gain in performance over no prompt. That's the sci-fact one. And then if you look at the overall results, Promptriever gets a 1.4 gain on beer just by using this prompt. Whereas if you choose the best prompt, even for this RepLlama model, you get actually a negative gain. And so it turns out that using instructions during training makes your model promptable when it doesn't for these models that don't use instructions. Cool. We can also look at the variance of these scores. So you could say, well, maybe like you just picked a really good prompt, the other prompts are all bad. Ideally, you'd want any of your prompts to be like fairly close in the same space. So models that understand prompts should have a lower variance. And that's what we see here. BM25 has a really wide variance. It is keyword search. RepLlama has 5, and then Promptriever has 2.8. I will say there's actually still a decent amount of variance. Some of these have like 5-point swings. And I think that's probably something that will improve with future work, but is definitely something to note. And so finally, which parts of this recipe help? So we did a bunch of ablations. I'm going to show on these 2 data sets the different components that make it work and some things we did to test what it was. So first off, one could argue, well, maybe it's just that you had really long queries during training. And if you just trained your model with really long queries, it would get some of this performance. So for that, we tested repeating the query n times, or just using a generic instruction like I had GPT and Claude generate these, but something like find a relevant document and those sort of generic instructions. And it turns out if you do that, you really don't get that much help. Roughly the same, maybe you get a small performance gain for those generic instructions, but not much. Or maybe you could argue, well, it's the distribution of instructions that make it better. So what I did is I generated the instructions and then I swapped their ordering with the queries. So you have a random instruction with a random query just to learn the distribution. And you can see there actually is a somewhat gain. You get about a 2-point gain in PMRR, but still not that much performance gain. It's still negative. If you add instructions, you get a pretty large gain there. If you have the mapping between the correct query and the correct instruction. And then finally, if you add these instruction negatives, you get a pretty nice gain as well. And then our final model adds back in the regular MS Marco data. So it's not just instructions, it has instructions plus all the MS Marco data. Cool. So yeah, in summary, promptable retrievers show large gains on instruction following tasks. They're able to see gains on standard retrieval tasks as well, just by adding a prompt, just like you would do for a language model. And then this training data can be constructed with synthetic generation, which is great because you can't really find it out on the internet alone. This works great on 7B plus models, Llama Mistral. We have results for all of these. I haven't been able to get it working well with BERT, which is a bit sad because I would like to get a small model working, but BERT is really, I guess, not a very good instruction model, and maybe it's not possible. So yeah, let's see, what's next for this? This is just MS Marco data, so you could easily scale this up. Modern retrieval models use a lot of data, and it's not really surprising, but science, code, not just web data. I'd love to see it be able to adapt to new relevance tasks on the fly. It's not super great at this right now. For example, if you typed in the query like, I want to find all things that talk about yellow objects, it probably wouldn't work super well, but I think that'd be a very cool type of task to enable with retrieval models. And then finally, better evaluation data. There's really only those two I've been using. It'd be nice to have some that really test comparisons, logic, these meta level queries I've been talking about. Cool, yeah, thank you.
I wonder what you think about course defined retrieval. It seems like what you really want is to map a query or a set of instructions to some way of finding relevant documents, and that might include a probe that you use to get back, 150 candidates, but then also some other parameters that you would use to look at the version embeddings or something of those candidates to decide which ones you like.
Yeah, great question. And I think any modern production system will do that, right? You're going to run it on the first and oh, okay, yeah.
So you can educate all of us.
Yeah, you're gonna, if you have a production system, right, like SearchGPT, they actually first use Bing's index. So you're first gonna hit Bing, get back the first 1,000-ish, maybe 10,000 candidates. Then you're gonna run some other re-ranker on top of it, and then finally pass in the top only really high quality end to GPT-4. And so I think, with this, GPT-4 is gonna be better at following your instructions than a retriever all the time. Like there's no way that's not gonna be the case. But in the case you have billions of documents, you can't use GPT-4 on all of them. So improving that capability helps you at the early stages to give you those documents that then you can then filter up.
Okay, yeah. So what you just described is, of course, defined architecture.
Yeah.
But there was a big jump between doing a vector retrieval, vector re-ranking on the things that came back from Bing and throwing GPT-4 at them. Could there be something intermediate where from the instructions, you're predicting the parameters of a neural net that scores the document?
Yeah, absolutely.
So just doing an inner product, I guess that's a neural net, but it's an incredibly shallow one.
Yeah, that kind of middle step of a re-ranker, a cross encoder before you give it to GPT-4, absolutely. And that was one of the follower 7B ones I showed. It could be used as that intermediate step.
So for building a training data set, you said you couldn't get type GPT-4 to give you very matched but not instruction matched documents and so on. And you said you did filtering some of them. Like, what was the size of the training data set? What did you do?
Yeah, I glossed over a lot of that. No one wants to hear about the data cleaning, right? That's the least fun part. So we generated 3 instruction negatives per query. There's 500,000 queries. And then only like 2/3 of those were actually good. So we used the follower 7B model to filter them. I think there's probably still a lot of false positives, false negatives, but it was good enough for that. But yeah, that'd be something on the order of what, 1 million instruction negatives. Luckily, the internship paid for that.
Part of what Jason was suggesting, if you want to do something course defined between like the re-ranking that Bing does on its own internally versus this one, right? So a good course defined method has this property that in the intermediate steps, there are no false negatives. You can always have pretty low precision, but you need to keep 100% recall so that the next thing doesn't do that thing. Do you know if the things you're playing with or whatever you suggested as an intermediate step either has or can be tuned to have very low false negatives?
False negatives. So to have high recall without low precision?
Precision is not great because after all, you've got 5,000 and you want to reduce it to 1,000.
Yeah.
Just don't lose the 100 relevant.
Yeah.
The 5,000. Do you know if any of your methods are tunable that way, or do you need to have that property?
Yeah, that's a great question. One thing we talked about during the internship I never got around to is I'd love to be able to put in a prompt to be able to tune that and say like, I really care about high recall right now, like give me everything, or I really care about high precision. If you think it's maybe not relevant, drop the score. I don't think it's that tunable yet, but it would be nice if it was.